yeah, some of the previous discussion is a nice segue into what I'd like to talk about. I'd like to thank the people who put together this meeting, giving me a chance to talk. It actually gives me a chance to talk about some of the work I did when I was doing my PhD. I finished in Waslab about 2 years ago, and so been at GATAN for a couple of years now. But that work was sort of on the tail end of my PhD, so I never really got a chance to talk about it. So I'll talk to you about some of the work characterizing CCDs that I did today, or I did at that time actually, and some of the products that, or some of the things that happened since then. So what I'd like to talk about today are sort of the development of what we're calling the GATAN's U-type scintillator. So this is our high-resolution camera for low-dose imaging. And then I'd like to introduce another camera that we've designed for collecting diffraction patterns. So it's actually a new camera, just released in August. So I'll just show you some early data from that. So I was pleasantly surprised to hear such an endorsement of CCD cameras for electron diffraction. I think people recognize that there are a lot of advantages using CCD cameras. And the dynamic range with linearity. And what keeps coming up though is that the scintillator gets in there and it causes a problem with the point spread function, the MTF. And what I want to show you today is that there are some recent results that I'd like to talk about that show that this problem isn't as severe as we thought previously. So what's going on here? So this is what a bottom mount, so a CCD camera sitting in the bottom looks like. It's got a scintillator on top. There's a fiber optic which transmits the light from the scintillator down to the CCD camera. And if you look at just this region here, this is just a Monte Carlo simulation of electrons striking the scintillator and then decaying through the fiber optic material. And so this is kind of, and the scale here is the simulation as you increase the accelerating voltage. So as you go to higher and higher accelerating voltages, you get more and more decay of these electrons, and everywhere where these electrons strike the scintillator, you're getting light transmitted. So even though most of the light, I should point out, this is a log scale, so it looks worse than it is, but it definitely is a problem. And everywhere where the electrons strike the scintillator, we're getting light emitted, and so a single electron band isn't actually constrained to a single location. And so that's what we're struggling with. So what's one way we detect that? Well, what you can do is you can image something, an image of something, an amorphous material. You can do a Fourier transform of that and look at the tone rings. And this decay or fall off sort of gives you an indication of how much blurring is going on in this image. So this is, the reason I bring this metric up is because this is a way that we pretty routinely looked at when we're doing biological cryo-EM. It's something we did routinely, we did it every day. And so it turns out that this is one way which we can start to approach what the blurring out looks like. So from the comments in the previous talk, there are a lot of ways to measure this blurring. There's people talk about the point spread function, which is it's straightforward to understand. It's that blurring. If you thought of it as something striking a single point, it's the blurring that occurs about that single point. We talked about the modulation transfer function, the MTF, which is the Fourier transform of the point spread function. And I appreciate the comment earlier. The MTF is not the same thing as the NTF, which if you're taking a flat field image and you're doing a Fourier transform of that, which is what the NTF is, it can look a lot better than you're justified in believing. So if you had a very noisy detector, the NTF would look really good, and you'd fool yourself into thinking you had higher image quality, when in fact it's actually poorer. And so this metric, when that gets confused, it's difficult sometimes to compare apples to apples. So at GATAN, what we do is we always use detective quantum efficiency as a function of spatial frequency. Now, people don't, and what it is the MTF sort of normalized to you can think about it like the MTF normalized to this noise transfer function. So noise varies as a function of spatial frequency, and that, and if we normalize to that, that gives us a measure of the signal quality we have at every spatial frequency. And that's what we use internally to evaluate our cameras. Now, what Waslab used is this spectral signal noise ratio, which is it's a familiar idea to the cryo-EM community. The real downside to it, though, is it mixes contributions of the microscope with the sample and of the detector. So if you're trying to assess a detector, you have to be very careful when using this to make sure that you're not mixing different, you're making sure that everything's staying the same if you're using it to compare detectors. So that's just something to keep in mind. But if you have done that, it's relatively straightforward to understand. So I showed this image before, and the fall off of the tone rings that I talked about, if you have the luxury of going to high dose, then you're fine. You don't need to worry about this because you can get enough signal at high spatial frequency that you can use it. But if you're operating at lower electron, so this is the electron dosage in the top, in the corners here, and as you work at lower dose, that's when you really start to get hit by this point spread function, the MTF, and that's why we have to worry about it in this community here. So I said before, the first method that we were using in WASLab was one where we were fitting a background curve to a rotationally averaged power spectra, and then we were subtracting the power spectra from the background curve to give us a measure of signal to noise ratio. And this is just what it would look like, and that's what we used to compare that. And so in 2002, this is when I was brand new. This is sort of the latest, greatest CCD camera we got installed in the lab. And the first thing we did was do this kind of comparison. We took some image to carbon film and compared the two. And so you can see that actually at high spatial frequency, film was beating out the CCD camera. And so at this point in time, it was definitely correct to say that the film was performing better than the CCD camera. Nevertheless, we went ahead and we, what I'd like to tell you, the data I just showed is from this early ultrascan, or not early, this ultrascan camera that we had in about 2002. And I'm going to tell you about another ultrascan camera that was sort of a result of an optimization project for us to create a scintillator that would work really well at 300 kilovolts. And so that's what I'm going to discuss in this first part of the talk. So looking at this image again, you can see out at half Nyquist frequency, film is definitely beating out the CCD camera in terms of performance. So nevertheless, we went ahead and we took images of that, and we did a reconstruction. And somewhere around 2/5 Nyquist frequency, so we did a reconstruction, and the resolution that we assessed of the reconstruction used about 2/5, landed about 2/5 Nyquist frequency on the CCD camera. So we were getting a little less than 2 pixels, effective pixels, if we want to use that terminology. And I just put this image here to show you that when you see these curves, they don't always mean that that's the actual resolution. So if you look at the data and you see features that you expect at that resolution, then you can start to believe it. Okay, so from this point, we worked closely with this group, and we had a challenge that we need to create a CCD camera that would allow this kind of imaging at 300 kilovolts. And so internally what we do is we had a bunch of cameras being produced, and we made careful measurements of different parameters in the camera, and we evaluated them all using this DQE term. So using DQE, we came up with a camera that we thought would be really ideal for this particular application. So the camera was produced, and this slide just goes up to show you when you're moving from 200 to 300 kV, it really gets worse. The MTF of these cameras, it's a lot harder to localize the electrons right around the scintillator. So this is a difficult challenge for us, and that's why we took it on. So when the camera was finally made and came back to WASLab, we did exactly the same kind of analysis that I described previously. And what you're looking at here, the legend seems to be gone, but red is the CCD and black is film, and we were really shocked to see that out at half Nyquist frequency and beyond, the CCD seemed to be performing as well as film. And so the first thing, we didn't believe it actually, so we did it again. And this is at a lower dose, and we saw that at higher spatial frequency, the CCD camera was really performing as well as film. And so we kind of weren't sure what to make of it, we got excited. We ended up publishing this work, and then about that time, that's when I left WASLab and joined GATAN. So fortunately for me, Donghua Chen carried on and collected a data set on this camera at 300 kilovolts. And the nice thing he did about this was that he collected this data set on, this is epsilon 15, so it's their favorite test specimen. But he did this experiment at a very low magnification. And then what that allowed us to do was it allowed us to sort of take some of the questions we had about this process out of the equation. So we knew the microscope was going to be good at this mag. We knew that the reconstruction algorithms were going to be good at this mag. So when they did the reconstruction, you can see that I think this was 40, 50,000 mag. It was, I've got it written down in a slide later. But the assessed quality of this reconstruction ends up being at about 2/3 Nyquist frequency. So well past half Nyquist frequency. And what that means is that this CCD camera was giving us enough information at that spatial frequency to give us a reconstruction at 8 angstroms resolution. So and just to put that in perspective, if we take a look at some of the other reconstructions that happened at that are less than 1 nanometer resolution, you can see that this is the reconstruction I'm talking about right here. So compared to other reconstructions at 300 kilovolts, we are at almost half the magnification, and we were able to achieve a similar sort of resolution. And so that speaks to the improvements to this type of simulator for working at 300 kilovolts in a very practical way. So we're about 2/3 Nyquist frequency there. So, and this one here is the first one we did. The one I talked is CCD camera A that I talked about previously. So we were about 2/5 Nyquist frequency. And so, despite the fact we went up to 300 kilovolts, we were able to see an improvement in usable pixels. So, because this is a crystallography meeting, I was also fortunate that Benoit Chen took the time to image bacterial rhodopsin on the CCD camera. And so this is just an image of one of the crystals. There's no unbending on this one. And the ring represents about 9 angstroms resolution. And so they, without unbending, they were able to see features or spots out at 9 angstroms resolution. And if they go ahead and do unbending and do an IQ plot, you can see that, so this represents 4 angstroms out here. And they assessed the data to be about, they had quality data out to about 5.8 angstroms resolution on this camera. So so what they did is they measured the phase residual between their data set and the published structure. And so using that, they determined that at this magnification, or at this camera, at this magnification, they were able to work out data, get data to about 5.8 angstrom resolution, which is similar to the 2/3 Nyquist frequency number that I talked about before.
What is the peak size of this mag?
So this mag was 84, so I think it's about 1.8. It's on the order of 1.8 angstrom pixels. So, and this is images of the crystal, and then we're looking at the transform of those images. So that's what we're right. And then this is after unbending. Okay. So with that, I'd like to just introduce a second camera, which is really designed to be used for electron diffraction, so collecting diffraction patterns. So the features of this particular camera are that it's a top-mount camera. It has relatively small pixels, but because it's a top-mount camera, it has a pretty large field of view. So it sits up there, and the field of view is comparable to that of film. Okay. Now there's two really key parts to this camera. The first part is that it's got a scintillator that's designed to be resistant to electron damage. So I'll show you some of the images, but what that means is that you can start to image without a beam stock on this camera as well. And the second one is that we've got there's a method to reduce or to eliminate the streaks that happen when you oversaturate pixels on this particular CCD camera. So again, this is a high frame rate camera, so it sits in the top mount port, so it's really complementary to the ultrascans that sit in the bottom. You could think about combining using this camera for high frame rate stuff and collecting diffraction patterns, and the other ones for your high resolution imaging. So, right, and this is a lens coupled, the top mount. So, unfortunately, it's new enough that we don't have any images of bacterial rhodopsin or biological specimens to show you.
Can you go back to this?
Yeah, of course.
Lens coupled.
Well, it's
So with the
yeah.
So I thought this lens coupled thing is ultra difficult to do, and you need a huge active focusing of that, and so.
Well, so it's more. I think it's let's see. I mean, this is standard part of these
the
top mount
resolution
cameras.
in the corners of field of view the same as in the center.
The resolution of the corners.
So you don't have a full aperture of the lens is available.
Yeah, interesting. So why don't I don't know the answer to that actually, but I can I can put you in touch with the person who will know the answer to that.
Okay.
What is the size of the CCD here?
So this is a 2K by 2K CCD.
2K.
Yeah, that's right. And
30 microns.
pixels? No, like
7.
50.
yeah, 7 I think.
That's 7. Huh?
Yeah,
Oh,
yeah, very small, very small. Yeah. So the idea is that it's not it sits in an area that's not larger than what film would image, and that way any S-type distortions shouldn't show up. That's the idea. Okay, so this is an example of an image, a diffraction pattern of what is this? Yeah, where there's no beam stop being used, and we've actually saturated some of the central pixels. And you can see that in this case, we're not seeing the streaking that you'd expect to see by saturating the pixels on a CCD camera. I have, let's see, one more showing sort of the same thing. It's a different, different imaging conditions, but you can see that the central spot, you don't have useful information in this region, but it doesn't destroy the region surrounding there. And then lastly, just a couple of shots of a crystal, using selective diffraction. I think, some lanthanum, cobalt, and just towards the edge of the camera, we're still seeing spots available. So this just to introduce you to a camera that's that was the bin data. I apologize. So it's not really telling the story. This is the unbin data. So you can see out towards the edge of the image there you can start to see the spots show up. So yeah, this is a camera which is designed with electron diffraction in mind, and we'd love to see some examples of biological data on the camera with this. So just to summarize, we're really trying to be driven by customer metrics. So in this case, we can optimize the camera for 300 kilovolts. The lessons we learned in this project have been in our products for at least 2 years now, and we'll continue these kinds of improvements will be in the future generation of cameras that we have. And again, customer benchmarks are driving what we need. So people were finding that they put something new in a microscope and they wanted to click the diffraction pattern, and they had a nice spot on their CCD. So this is one way to help avoid that. So thank you for your attention.
I still have the same question which I asked you before, and why this camera is better. I know you will not give me the answer, so I'll ask a different question.
Maybe you'll trick me. Let's see.
So, I assume that I understand that you use this signal noise ratio to measure your camera, but do you also measure the MTF and DQE and all these things of this camera?
So
compare with the other camera or your other GATAN camera or this camera. What I mean, show.
Sure. So the internally we don't use spectral signal noise ratio. We use DQE, and a part of calculating DQE is making sure you measure MTFs and NTFs. So we have those for most of our cameras. So
But for this particular one, is it better?
Oh, is the DQE better?
Yeah,
no question.
How much better than the?
Let's see.
Compare with because this is kind of
Well, so Paul is starting to quote specs on these in terms of DQE at certain fractions of Nyquist, and I will let you talk to him directly to get exactly what those numbers, the differences. But you'll start to see those numbers when you're looking at a camera spec. You'll see DQE at half Nyquist or some fraction of Nyquist frequency. You'll see whatever percentage of the quote.
So following on from that,
Sure.
as we've got all these people in the room like Bob and Ken who know this subject, is there one measure that one could give the public to be able to evaluate CCD cameras properly? Is it DQE, for example?
I mean, according to us, we'd love to have everybody adopt DQE. DQE it's an old metric. It's not ours. I mean, it developed I think in the 60s or something. I mean, but it really became popular in medical imaging when they were developing CCD cameras, and they were seeing better images, but they weren't measuring better NTFs.
But as a customer, customers, you look at it, it's so many different numbers. Everybody's measuring something different. It's really hard to compare.
Right.
What would be the best way of, if you had to use one or maybe two numbers, what would they be?
I mean, it depends on your application. I mean, we believe in this metric, and this is a metric we've seen improve our cameras. And we can give you numbers like MTF, but we don't think it tells you the whole story. So it's, I mean, I don't, if you have a preferred metric, we can try and give you information however it makes sense to you. I mean, yeah.
I think there will always be different people who have, different parts of their experiment are the most important ones. And so they will use whatever is best suited to it. My personal one, having told you, is how many pixels do you have at spatial frequency that where the MTF falls to 0.5. If you could scroll back to the slide that showed the CTF, the circular
Sure.
CTF without the background subtracted.
Oh.
Keep going.
This one here?
Yeah.
Okay, yeah.
Yeah. So I just wanted to point out to people in general that where the CTF goes to zero, so to speak, that's where the background is put in.
Right.
There is no contribution from signal there.
Right.
So the Fourier amplitude that's present there is only from the noise.
Yes.
So this background curve is your noise transfer function. And it doesn't roll off nearly as fast as the MTF does.
Right, right. You can see the fall off like this is sharp, whereas this one is falling off much less sharp.
So the maxima of the tone rings, very good measure of the MTF, especially once you subtract the noise transfer function.
But is there, with the metric you were suggesting to Henning about the 0.5 cutoff, could that be improved by incorporation of some of the fall up of the noise as well, or is that then not necessary?
It's a good argument for the normalization that Chris pointed out. You divide one by the other, and that's called the resolution or the frequency dependent detective quantum efficiency.
So that's DQE. I was wondering if you use.
It's hard to wrap your mind around what does that mean, but that is becoming essentially the standard for comparing.
Well, I would say the old frequency independent measure of DQE is really outmoded, and there's a lot more to gain from the frequency dependent DQE. I think that's probably what's most important for most people. I don't see the 0.5 cutoff in MTF as a hard and fast limit. It's a useful number, but the fact is that we use film way beyond where it has an MTF of 0.5 probably. But if you're a material scientist, you're probably not so concerned about the noise level of the camera, maybe more about the MTF than the DQE. So it does depend a little bit on exactly what you're doing with it. If you're doing electron diffraction, your criteria would probably be very different from if you do it trying to do lattice imaging or single particle imaging, for example.
So your first camera that you used in Manchu for these virus projects, how many pixels did that have?
That was a 4K by 4K.
Okay.
Yeah, that's it was this. It was, I think.
The ultra scan 4000.
Yeah, it was Ultrascan 4000. It was one of the early Ultrascan 4000s. Triram had one before us, but it was one of the early ones. It was I think it was the first one where we're running at 200 kilovolts.
So we started doing an analysis of the number of asymmetric units, plotting asymmetric units for single particle analysis against resolution.
Yeah.
And we haven't finished that analysis, but some of the studies that came out were quite interesting in the sense that some of the CCD cameras seem to require a lot less than film. Can anybody else comment on that? Is that something that you're aware of, or is that just...
The CCD cameras require less what?
If you try and compare resolution against the number of asymmetric units required to achieve that resolution, it's a bit of an unfair comparison because sometimes you've got viruses and sometimes you've got macromolecular assemblies. But it was interesting to see that some of the virus reconstructions that were done seem to require a lot less particles than we did for some of the other film studies. But
That'd be very suspicious study.
okay.
Are these the same viruses or different
No, different viruses. So it might be just chunks.
You also have sort of like resolution, because a low resolution point release, contrast from CCT is better than the film, and which may help you for the alignment, or maybe you only consider relatively low, so I mean, it's
Yeah.
hard to say what is the level.
It's complicated.
Okay, any other questions? Well, please join me in thanking our speakers.
Thanks a lot.